AST along long span. ASTY is equal to 0.5 FCK divided by FY bracket 1 minus under root of 1 minus 4.6 MUY divided by FCK into B into dy square bracket close B into dy. So substitute all the value. 0.5 into FCK is 20, Fy is 4 and 5 bracket 1 minus under root of 1 minus 4.6 into MUY value you got was 10.25 into 10 to the power of 6 divided by FCK is 20, B is 1000, dy is 132 and B is 1000 and dy is 132. So here dy, how it comes? This is the slab of having the overall depth, that is 160 mm, and here this is the short span steel and the circle which you are seeing here is the long span steel. So from here to here it has the distance of dx, that is 140 mm. From here to here center of this bar is the this one, here to here is our dy value. So our effective depth value for longer span is here, center to center distance from this particular bar to here is our effective depth of longer span, that is denoted as dy. So for that what we have to do is we have to take the dx value. So from here to here we have know the dx value, effective depth value for shorter span, that is 140 minus the from here to here is the 140 minus 8 by 2. 8 is nothing but we have assumed the diameter 8. So this is already half, that's why I am taking minus 8 by 2 minus 8 by 2. Why? Because so 8 by 2 it is already half, so I am taking 8 by 2. So again we have to go half, that is minus 8 by 2. So by calculating our effective span value for longer span, it will come out as 132 mm. So to reach from here to here, make it as 8 by 2 and 8 by 2. So that's why this is how we have to calculate the effective depth for longer span. So from this particular diagram, this is how we will find out the dy value. So dx value we already taken, that is 140 by assuming the diameter, and from this particular figure we'll come to know the dy value as 132 mm. So this is how we calculate the dy value. So substitute here dy value as 132. So I have substituted. So by simplifying our ASTY area of steel along the longer span, it will come out as 253.44 mm square. So this is how we calculate the AST along longer span. And next is the check for the AST minimum. So as per clause 26.5.2.1 page number 48, we'll see. So minimum reinforcement. The mild steel reinforcement in either direction in slabs shall not be less than 0.15% of the total cross-section area. However, this value can be reduced to 0.12% when high strength deformed bars or welded wire fabrics are used. So what they have said, for deformed bars, that is nothing but Fe4 and 5, the value should be taken as AST minimum value should be taken as 1.2% into total area, that is nothing but 1.2% into B into D. So by using this we have to calculate the AST minimum. So as they are mentioned, for HYST bars 0.12% into B into D. So AST minimum is equal to 0.12% is nothing but 100 into 1000. B value is 1000 into overall depth we got was 160. So substitute all the value. By simplifying our AST minimum, it will come out as 192 mm square. So now, look at the value of our AST, area of steel along longer span as well as shorter span. So our area of shorter span is 319.2 and area of longer span is 253.44 mm square. So by seeing these two, we can conclude that our AST X and AST Y is greater than the AST minimum. So hence our design is okay. We can calculate further. So next we'll go to assuming the diameter to calculate the area. So I am assuming the 8 mm pi bars. We'll calculate the area. So AST is equal to pi by 4 into d square is nothing but diameter, that is 8 square. By simplifying, it will come out as 50.26 mm square. Now we'll have to calculate the spacing for short span as well as long span. So we'll see one by one. The spacing for short span, that is denoted as Sx. We have the formula. For that we have the formula 1000 into AST divided by AST X. So 1000 into AST, that is area we got was 50.26 divided by, so area of steel along the shorter span we got was 319.2. So by simplifying, it will come out spacing come out as 157.45 mm center to center. So that's why provide spacing is equal to 150 mm center to center along shorter span. So I am reducing 157 to 150 mm. Why I am reducing spacing is I have clearly told in my previous video. You can go for that. So now AST provided. So AST XP is equal to the area which we have calculated divided by spacing into 1000. So substitute all the value, though it will come out as 335.06 mm square is the AST provided. So similarly, we have to calculate the spacing for longer span. So SY is equal to AST 1000 divided by AST Y. 1000 into area we got was 50.26 divided by area of steel along the longer span we got how much, 253.44. So substitute all the value. By simplifying the spacing, the value will be 198.31 mm square. Now, so provide 190 mm center to center along longer span. So again I am reducing 198 to 190 mm. So I have explained why I am reducing it to 198 to 190 mm in my previous video. You can go through that video. So now here again we need to calculate the AST provided. For that we have the formula 1000 into AST divided by spacing. So substitute all the value. By simplifying, it will come out as 264.5 mm square is the AST provided. So this is how we calculate. So step 8 is to calculation of the shear stresses. For that, here also we need to calculate the twice shear force along the longer span as well as shorter span. So shear force formula we have Vux is equal to WLX divided by 2. So WU value we got was 10.5. So LX value was 4.14 divided by 2. By simplifying, it will come out as 21.73 kilonewton for short span. Now shear force for longer span, we have the formula WUY is equal to WULY divided by 2. So WU was 10.5 into LY value is 5.14 divided by 2. By simplifying, it will come out as 26.98 kilonewton. This is the value for longer span. So next we'll go for the calculation of nominal shear stress. that is denoted as tau v x. Vux divided by b into dx. So Vux just we got was 21.73 kilonewton. So substitute that value 21.73 into 10 to the power of 6 divided by 1000 into 140. It will come out as 0.13 Newton per mm square for short span. Similarly for long span, tau Vy is equal to Vuy divided by b into dy. So Vuy we got was 26.98 into 10 to the power of 3 divided by 1000 into dy value we got was 132. So substitute all the value. By simplifying, it will come out as 0.2 Newton per mm square for long span. This is how we calculate the shear stresses for short span as well as long span. So next we will go for the calculation of percentage of tension steel reinforcement. We have the formula PT is equal to ASTX into, this is the area of steel for short span. AST provided, we need to substitute the AST provided value for shorter span divided by b into dx into 100. So our AST provided v for shorter span we got was 335.06 divided by b is 1000 and dx is 140 into 100. By simplifying, it will come out as 0.23%. This is the value of Pt. So next we will go for the calculation of tau c value. Calculation of tau c value with the help of the Pt and FCK. By using the table number 19 which is given on page number 73, we will see. So our Pt value is 0.23. By using this value and our FCK is 20. These two will calculate the tau c value by doing the interpolation method. Table number 19, design shear strength of concrete tau c Newton per mm square. The first column has the value of Pt value. So our Pt value we got was 0.23. 0.23 means it comes in between 0.15 and 0.25. So for 0.15 we have the corresponding concrete value, that is 0.28. For 0.25 we have the value 0.36. By using this value and with the help of the interpolation method, we will calculate the tau c value. So the same value I have written here. For 0.15 we have the value 0.28. For 0.23 we need to calculate now, and 0.25 we have the value 0.36. So tau c is equal to, as usual, we have to take the least value, that is 0.28 plus, because the value is goes on increasing here, that's why we need to take the plus, into the greater value minus least value and the greater value minus least value, that is 0.36 minus 0.28 divided by 0.25 minus 0.15 into the value which you want to find out minus the least value, that is 0.23 minus 0.15. So substitute all the value. So by simplifying, it will come out as tau c value is equal to 0.34 Newton per mm square. Here one more thing is, so to check the 0.34, the value is lies in between these two, no? When it lies in between these two, hence our value is correct, because 0.34 comes in between 0.28 and 0.36. Our value is correct. So now what we have to do, so our tau v x value we got was 0.15 Newton per mm square and tau v value we got was 0.20 Newton per mm square. So by seeing these, we can conclude that our tau vx and tau v value is less than the tau c value. So hence the slab is safe in shear. This is how we conclude. So next we'll go for the check for the deflection control. So again we use the formula, the L by D ratio, which we have the L by D ratio. L divided by D max is equal to 20 into KT. So for this I will show the page number 37 of IS 456. Again we are applying this, which is we have used for the calculation of beams, designing of beams. The vertical deflection limits may generally be assumed to be satisfied provided that the span to effective depth ratio are not greater than the values obtained as below. Basic values of span to effective depth ratio for span up to 10 meter. Now we are calculating the simply supported slab. So for slab, the L by D ratio should not be greater than 20. So I am taking this. So L by D is equal to 20 into KT. KT is the modification factor. So which we have to calculate now. So to find out the KT, again we need to go for page number 37 of IS 456 to find out the KT value. I will show. So this chart you are seeing one chart here. By using this chart we need to calculate the KT value. So this is the percentage of tension steel reinforcement FS curve. To find out the KT value we need to have the two things, that is the value of per PT value and as well as FS value. So now we have the PT value but we don't have FS value. We need to calculate. To find out the FS value, they gave one formula here right below the chart, that is Fs is equal to 0.58 EFY into area of cross section of steel required divided by area of cross section of steel provided. So by using this formula we have to calculate the Fs value, and after calculation with the help of Fs value and PT we need to calculate the KT value. So we'll see. Same formula I have written here. Substitute all the value. 0.58 into Fy is 4 and 5. EST required is 319.2 divided by EST provided is 335.06. So here I am using the value of EST required for shorter span as well as EST provided of shorter span. Is equal to, by simplifying it will come out as 228.66 Newton per mm square as the Fs value. So now by using this value and with the help of PT we will calculate the KT. We will see. So our PT value we got was 0.23. 0.23 means it comes here in between 4 and 0.4. The value Fs value we got was 220. Fs value we got was 228. 228 means it comes near this curve Fs 240. So by using this curve and with the value of PT we will calculate the modification factor. So now here our value PT value comes here 0.23. It is PT value is 0.23. It comes here. The line where it cuts the curve and right left 2 is our modification factor. So it cuts here. So here to here it comes around 1.6 is our modification factor. Straight to this. States here. From here it touches here to straight to this curve is our modification factor. It comes near 1.6. So now substitute KT value in above equation. So L by D max is equal to 20 into 1.6. It will come out as 32. We need to calculate the L by D actual. So L we got was 4140 divided by 140 D value is. So it will come out as 29.59. So by seeing these two, what we can conclude that? We can conclude our L by D max is greater than the L by D actual. And see our deflection is within permissible limit. This is how we calculate the deflection control. So next, the last step is check for the development length. So again, as per code book rule, for simply support, we'll go for the page number 44, clause number 26.2.3.3. We'll see page number has simple supports and a point of inflection. Positive moment tension reinforcement shall be limited to a diameter such that LD computed for FD by 26.2.1 does not exceeded M1 by V plus L0. And here The value of m1 by v in the above expression may be increased by 30% when the ends of the reinforcement are confined by a compressive reaction. So what they have mentioned, the value of m1 by v is again going to increase by 30%. So we'll see. So L0 is less than or equal to 1.3 into m1 divided by v plus L0. So for m1 we have the formula 0.87 Fy AHT1 into d minus 0.42 into xu. For here what is unknown? AHT1 is unknown. To find out the AHT1, we need to, for that we have the formula AHT provided divided by 2. This is the AHT1 is nothing but half of the AHT provided. So AHT provided we got was 335.09 divided by 2. So it will come out as 167.54 mm square. So here I am putting the value of AHT provided for the short span. So it will come out 167.54 mm square as the AHT1. So now here XU is unknown. For that we have the formula XU is equal to 0.87 Fy AHT1 divided by 0.36 FCK into B. This formula is given in code book. So substitute all the value. 0.87 into Fy is 4 and 5. AHT1 we got was 167.54 divided by 0.36 into FCK is 20, B is 1000. So after simplifying it the answer will be 8.4 mm. So now we have the value of AHT1 and D and XU. So everything we have calculated. So substitute in this formula. So m1 is equal to 0.87, Fy was 4 and 5 and AHT we got was 167.54, D is 140 minus 0.42 into XU we got was 8.4. Substitute by simplifying, we'll get answer as 825523.542 Newton mm. So now here the V value, shear force value we calculated, we got was 21.73 into 10 to the power of 3 Newton. So we have the value of m1 and V. So now substitute in this formula. Now we have to calculate the L0 value also. For that again we need to go for the code book, page number 44. This is the page number 44. For L0 value, the L0 is limited to the effective depth of the members or 12 pi, whichever is greater. So what they have mentioned, to find out the L0, the value should be 25 or effective depth of the member, either D or 12 pi. We have to consider the value, the greater value, which is the greater, we should take that value. We'll see. So we need to apply this condition. So now by applying that parameter, L0 is equal to D or either 12 pi. So effective depth we got was 140 mm. And now the 12 pi value by substituting will get 12 into pi diameter. I have taken 8. So by simplifying it will come out 72 mm. So they have clearly mentioned in clause our L0 value should be greater value. So which is greater? 140 mm is greater. So I am taking L0 value as 140 mm. So now substitute all the value in the equation, that is 1.3 into m1 divided by v plus L0. So 1.3 into m1 value we got was 8255.234.542 divided by v value we got was 21.73 into 10 to the power of 3. So L0 value just now we got was 140. By simplifying, the answer will be 633.87 mm. Call it as equation number 1. So now to find out the LD, again we will go for page number 42. This is the page number 42 of IS 456. LD, development length of bars. The development length LD is given by the formula LD is equal to pi rho s divided by 4 into tau BD, where pi is the diameter of the bar, rho s is the stress in bar at the section considered at designed load tau BD is a design boundary which is given on the table number here 26.2.11. So to calculate the tau BD value, we need to refer the table number 26.2.11. So grade of concrete given is 20. So for 20 we have the design boundaries value as 1.2 Newton per mm square. So we need to take tau BD value as 1.2. Now substitute all the value. So rho s value is nothing all the value 0.87 into 415. So rho s is nothing but 0.87 into Fy. Fy is 415, diameter 8 divided by 4 into tau BD value 1.2. By simplifying it will come out as 601.75 mm. Call it as equation number 2. Now compare the equation 1 and equation 2. By seeing our LD value we got was 601.75 and our M1 1.3 into M1 divided by V plus L0. The value which we got was 633.87. By seeing these two, we can say that our LD value is less than the 1.3 into M1 divided by V plus L0. Hence, our design is safe. It's safe in. This is how we calculate the development length. This is the last step of this problem. So now we will go for the drawing. This is the shortest span diagram of two-way slab having the overall depth 160 mm and effective depth of 140 mm, having the length of 4 meter and having the effective length of 4.14 meter and 230 mm wall thickness on both sides. The short span of 8 mm at 150 mm center to center and long span of 8 mm at 190 mm center to center. This is the short span and these are the long span, and the alternate bars of short span can be bent off 0.15 times of Lx from the center of the support. So which is nothing but 0.15 into Lx we got was 4.14. By simplifying it will come out as 0.621 meter. So this is the short span diagram of two-way slab. We will see the long span diagram of two-way slab. This is the long span diagram of two-way slab having the overall depth again 160 mm, the effective depth of 140 mm, having the length 5 meter and the effective length is 5.14 meter from here to here, and having the 230 mm wall thickness on both sides. The short span of 8 mm at 150 mm center to center and long span of 8 mm at 190 mm center to center. The alternate bars of long span can be bent off 0.15 times of Ly from center of the support. That is nothing but 0.15 into Ly value is 5.14. By simplifying it will come out as 0.771 meter. So this is the diagram of the long span of two-way slab. Long span diagram of two-way slab. So this is how the representation of the longer span diagram as well as shorter. This is the shortest span diagram of two-way slab and this is the representation of the longer span diagram of the two-way slab. I hope you understood. So if you like the video, like it and share it. Subscribe for the more videos. Thank you for watching.